This is the screencast for section 4.6, example 3, a highway chase. Ooh, how exciting. Okay, a police cruiser approaching a right-angled intersection from the north. So here's our intersection, and the police cruiser is coming in from the north. He's going that way. Has turned the corner and is now, is chasing a speeding car that has turned the corner and is now moving straight east. So the speeding car is going straight east. The police determine with radar that the distance between them and the car is increasing at 20 miles an hour. The distance between the police and the car is increasing at 20 miles an hour. So that means dz dt, the change in what the problem is already calling z, so I don't have to define that, is 20 miles an hour. If the cruiser is moving at 60 miles an hour, so that means the cruiser is moving at 60 miles an hour, what is the speed of the car? So we're trying to find dx dt, the speed of the car, how fast this is changing. And that's going to be a positive speed, but we're going to use a negative, velocity, I guess, for y, because the cruiser is closing in on the intersection, whereas the speeding car is going away from the intersection and the distance is getting bigger. So I want to use a, for this cruiser, not 60 miles an hour, but negative 60 miles an hour. So now a good setup here, if I'm talking about three sides of a right triangle would be Pythagorean theorem. Now x, y, and z are all functions of time. They are all changing. The distance of the speeding car from the intersection, the cruiser from the intersection, and the speeding car from the cruiser are all changing. So they're all functions of t. So I'm going to say y of t squared plus x of t squared equals z of t squared. So now I'm going to take the derivative, and I get 2y of t now to the first power, but then times dy dt, the rate that y is changing, plus 2x of t dx dt equals 2z of t dz dt. So now I got to plug in some numbers. Let's see here. 2 and then y of t. Well, let's see. The cruiser is 0.6 miles, so y is 0.6. dy dt we said was going to be negative 60 miles an hour because, again, the cruiser is closing in versus the speeding car, which is going away from the intersection. Plus 2 times x of t, we said the speeding car is 0.8 miles, so x is 0.8 at this instant we're talking about. It's going to change, but right now it's 0.8. Dx dt, the speed that the cruiser is, or the speeding car is going, we don't know, so we're actually still looking for that. Then we have 2 times z. We don't actually know z. It didn't tell us, but I can use Pythagorean theorem for this instant and figure it out what it is. So y of t, or y at this instant is 0.6, so that's squared, plus x at this instant squared, so 0.8, is going to equal z at this instant squared. Now z could technically be plus or minus 1, but because it's distance, we're only going to say that that's positive 1. So z is 1, and then dz dt from the problem said that that was 20 miles an hour. So now I solve for dx dt. So the speeding car is going 70 miles an hour, and if you remember, the cruiser is only going 60 miles an hour, so that cruiser better pick it up, otherwise it's never going to catch that speeding car. Now, the cruiser is approaching the intersection, so maybe they're slowing down. I don't know. And now try problem number 13, air traffic control. An airplane is flying at an altitude of 7 miles and passes directly over a radar antenna shown in the figure. So here's this radar antenna, and then the airplane's path technically passes right over that. When the plane is 10 miles from the antenna, so the plane is exactly 10 miles from the antenna. That's not up and over, that's not over. The plane connecting the antenna, so S here, equals 10. It actually says S equals 10. The radar detects that the distance S is changing at the rate of 300 miles per hour. So that means ds dt is 300 miles per hour. It's asking what is the speed of the airplane at that moment. So we're trying to find then dx dt, the speed that x is changing, the distance from a fixed spot to the airplane. So let's see, I know three sides of a right triangle, so again I'm dealing with Pythagorean theorem. But the difference between this problem and the example is that the height is staying the same. So in my Pythagorean theorem, I'm actually going to keep that in consideration. So I'm going to say 7 squared, because that is fixed, plus x of t squared. That is a function. It's changing depending on what time it is. And then equals s of t squared, the hypotenuse. Now, the height is fixed, so its derivative is 0. Its change in height is 0. The height is not changing at all. So that's why 7 squared, 49, its derivative is 0. We don't need to worry about that. Now we'll put down the derivative of x of t squared. So that's 2x of t dx dt equals, and then the derivative here, 2s of t ds dt. And now we'll fill in some missing information. Well, the first thing I come across is x that I don't know, so I got to use Pythagorean theorem off to the side again. 7 squared plus x squared equals 10 squared, because at this instant, the height is 7, always will be, but the s value is 10, so I got to find that x value. So I get that x at this instant, x at this specific time, is square root 51. So I'm going to put down 2 square root 51. dx dt is what we're looking for, so I could just leave that as dx dt, equals 2 times, now s's length is 10, said the problem. ds dt, also the problem said that the distance between the plane and the radar thing are, or antenna I guess, 300, it's changing at 300 miles an hour. So now I can just solve for dx dt. And I get that the airplane is going about 420.08 miles an hour, which I guess sounds reasonable for an airplane. I know they go really fast. And if this guy's changing at 300 miles an hour, 420 seems reasonable.